Hey everybody, welcome back for the 8th and final installment of this performance-based liquefaction hazard analysis series. And in this series, I'm going to walk you through the tools that we developed so that you could apply all of those simplified performance-based liquefaction hazard analysis methods that we talked about in the previous lecture in your own projects. And we spent quite a bit of time and effort developing these tools, but we think they're running great. As with any new tool, there's probably some bugs that are lingering, and of course, we'll discover those as time and practice goes on, and we'll eliminate those and put out some new updates. But for the time being, the software seems to be working well. So let me introduce you to a spreadsheet that we call CPTLiq. This is for simplified performance-based liquefaction analysis. And I really need to acknowledge two former graduate students of mine, Jingwen He, who is now at the University of Texas doing a PhD with Ellen Rathje, and Jenny Blomquist, who recently accepted a PhD position at Utah State University, and I believe she may be working with Dr. Brady Cox, so we'll see what time reveals there. But this is dated November 2020, and that's really the version when version 1.1 was created. We're well on, we're in version 1.41 now, and we've made many corrections and improvements along the way. Believe me, we've come a long way with this thing. So what I like to do is just kind of give you a walkthrough with the layout of this. So this is the intro page, and it just talks about our sponsors, the university and such. And then you can see all these different tabs down here. There's the Inputs tab, Final Summary tab, References, there's the Soil Info tab, Map Help tab, PB liquefaction initiation. PB is not peanut butter, it's performance-based. So performance-based liquefaction initiation, deterministic liquefaction initiation, performance-based settlement, deterministic settlement, performance-based lateral spread, deterministic lateral spread. There is a tab we call hidden. It's where we do a lot of calcs, but we unhid it so that people can go in and actually look at the numbers. We're trying to be as transparent as possible. And then version notes. So you'll notice right off the bat that there's different colors with these tabs, and that's because we're trying to color code everything. So I'm colorblind, so forgive me, but this color that I'm highlighting right here is for lateral spread. This color that looks red or pinkish to me is for settlement. This one that looks blue to me is for liquefaction initiation. And then these bright ones here, bright red and bright blue, these are the two, these are like the start point and the end point. These other ones are here for your help, so maybe we could go through those ones first. So the References tab, this is a tab that has just a bunch of information that is meant to help the user if they're struggling with concepts or don't really know what's going on. So we organize this tab according to liquefaction initiation and settlement, lateral spread displacement, CPT corrections, things like average shear wave velocity, stuff that we just pulled right out of code, and then we have actual references here from papers and theses and such, if anyone wants to look up any of these. And so this is a really useful resource for engineers out there who are just trying to understand some of the basic concepts. See, there's not a ton here, but again, this is just intended to be the most helpful stuff for you. There's this tab here that's Soil Info, and this is the brain, so to speak, of the spreadsheet. So all the info that you're going to put into the input page comes here to the brain, the Soil Info worksheet, and it's stored here and manipulated and used. And so this is where you can come and scroll through and see what calculations are being made, what the numbers are, and such. Everything is password protected, so you can't get in and change any of these formulas, but only the cells that are highlighted are technically you're supposed to change. But these ones, for instance, they have formulas in them too. So if you try to come in here and change anything on this spreadsheet, like if I try to change this number, you'll see that I get an error, right? It's protected. So we did that on purpose so that people can't come in here and really mess up everything we did and then complain to us later that the spreadsheet doesn't work. So the next thing I'll show you is just the Map Help tab. Now, this doesn't really apply anymore because we don't have physical maps. We used to have physical maps, but as you'll see, everything's moved to digital, and which is really, really useful and helpful. But we just left this here maybe as a reminder of how far we've come. I'll scroll over now to you can see what the hidden tab looks like. Again, this is just numbers. So those of you who are numbers and spreadsheet geeks will have a great time cruising around in that tab, but most people won't go in there. And then the version notes tab. This just talks about all the different versions that we've created and summarizes the bugs that we've fixed and such. Okay. So let's just jump right into the inputs page. This is where most engineers are going to spend their time, and this is what the inputs page looks like. And you can see that we tried to create it in a way that really suits the engineer who's using it on a project or a student who's using it on a homework assignment, where you have all the information about your company, the site location, project name, project number, who did it, who checked it, dates, even the CPT sounding name, all of those things. Those are very, very useful. We have as well, by the way, I should point out that every cell that has a color in it is a cell that is not protected. So you can change those values. If you try to change any other value, any of the white space that's on the spreadsheet, it'll give you again the same warning that you can't do that. So the spreadsheet's kind of built like a computer program. You can see for susceptibility characterization, we can define what we want the I sub C to be, we can define what we want the water level to be for design, what the water level was at the time we drilled or pushed the CPT. And these cells that have these little red, maybe you can see those little red tabs up in the corner. That means that there's a note with that cell. So if you hover over the cell, a little note will pop up. So this says I sub C susceptibility threshold. Default is 2.6. If the I sub C is larger than this value, the layers will be excluded from the analysis. So the research and the literature has shown that the I sub C that you should use for your susceptibility evaluations can really vary, and can vary quite a lot actually, from region to region or location to location. And so we allow you to be able to specify that. Now right here where it says start here, this is where you're intended to come in and just copy and paste your CPT log data. So we can change the units. So right now the units are set to US customary, as you can see. Maybe I'll zoom in a little bit so that it's not quite as small for you. So right now units are set to US units. So you see everything is feet, tons per square foot, tons per square foot, tons per square foot. If I were to change this to 1, then it would be it would be SI units, so you could see now we're in meters, MPa, KPa, KPa. So if you're inputting data, you want to make sure that the data is input in these proper units, because if you're off on your units, it will throw everything else off. And these units are hard locked in, by the way. So So you will have to adjust your units before you paste them into the spreadsheet. But we have the depth to the reading, the raw CPT tip resistance, the raw friction value from the friction sleeve, and the raw measured pore pressure if you have a piezo cone. Now, here in non-liq, this option allows users to manually identify layers that they do not think will liquefy. So there's a way that you can literally turn off layers. Even if they are liquefiable, you can turn them off manually. It's like, say you're going to do ground improvement in that layer, so you're assuming that layer will not liquefy, so you want to get rid of it in your analysis. So you can do that. So the way that you do that is, as you read here, you just enter the words or the letters NL for no liquefaction or non-liquefiable. And every layer or every cell that you enter NL into, it will exclude from the analysis. Okay. Right now you see I don't have any cells that have NL in them here. So everything is fair game. I can specify the return period. This is more just for the record keeping. These cells don't actually do anything. But right now, with the maps, the reference parameter maps that we developed, there are only 3 options. 475 years, that corresponds to a 10% probability in 50 years. 1,033 years, which corresponds to a 7% probability of exceedance in 75 years, and 2475, which is a 2% probability of exceedance in 50 years. So again, changing that cell won't do anything, but it just helps you keep track of which one of these return periods you're trying to analyze. Now, everything is color-coded on these on this worksheet as well. Everything that has to do with liquefaction triggering is color-coded kind of in a blue color. Everything that has to do with settlement is color-coded this pinkish red, and everything with lateral spread is whatever that brownish color is. But you see they correspond to the same colors of these tabs down here. Okay, so that gives you a clue of when you put in an input where it's going to go and how it's going to be used in the calculations. You can see up here is a key which lays all of that out for you based on the color. So here's all the inputs that you have to put in. Everything from the peak ground acceleration that you get. This is what we use, but the PGA value is used to estimate an FPGA for the correction factors. Oh, that's right. So if we're using the code-based site amplification factors, FPGA, we took the tables from the AASHTO code and we built them into the spreadsheet. So you can turn this on in such a sense that it will, let's see if here it is, this FPGA calc. If FPGA calc is left at 1, it automatically calculates that site amplification factor for you. If you leave it or change it to 2, then you can manually enter your own amplification factor. So like if you did your own site response analysis for the site, you can amplify your ground motion however you want. So this PGA value is really intended to be a bedrock ground acceleration, preferably corresponding to 760 meters per second, consistent with the USGS. The magnitude is the mean magnitude from the deaggregation of the return period of interest. And don't use the modal magnitude for this, use the mean magnitude. And then you can specify what your site class is. Again, that's just for your records. Oh, and it's also used for your FPGA calculation if you're doing that automatically. These parameters here are your geometry parameters for the lateral spread calculation. And you can see that there's some instructions all throughout here. Okay, to help you find what the deaggregations are for your site in the United States, there's a little button here where if you press on the button, it will open up a website, open up your default browser, and take you to the USGS Unified Hazard Tool that you can use to calculate deaggregations for sites. So to do that, you want to make sure that you select one of the dynamic options. I recommend the most recent or updated dynamic option. So you can see the most updated one is this version 4.2. So go ahead and select that. Let's go ahead and just analyze the site for kicks and giggles here. This is the south part of Salt Lake City, and this is Interstate 15, the main transportation corridor through Salt Lake City. And let's pretend that we're analyzing this northbound bridge over 7200 South on I-15. So if I hover my mouse over that, that tells me that we're looking at a latitude. I'm looking down here in the bottom right. If you look at the latitude and longitude, I'm looking at a latitude of about 40.621 and a longitude of negative 111.904. So I'm probably going to forget those. 40.621, let's go ahead and go back and enter that in. 40.621 and negative 111.904. Negative 111.904. Perfect. I want the peak ground acceleration, and let's go ahead and analyze for the 2475 year return period. We're going to assume bedrock conditions 760 meters per second. And if I wanted to, I could compute the hazard curve. This is a really cool tool, by the way. If any of my chums over there at the USGS happen to be watching this video, I take my hat off to you, because this tool is really, really nice. Here's all the different hazard curves from the different spectral periods. Here's the multi-period response spectrum. Good stuff. What I'm going to do is skip down past that and go down to where it says deaggregation. I'm going to compute deaggregation down here. And it's going to calculate the deaggregation that corresponds to the return period that I selected. And the return period I selected was 2475 years. So here it is. So it breaks it down by closest distance, the rupture distance, and moment magnitude, and the percent contribution to that probabilistic hazard. So if I come down here, here's the summary statistics for my deaggregation. This PGA ground motion is the PGA value I'm going to enter into my spreadsheet. So that's 0.636 or so. And then I'm going to come down here to my means. Mean of magnitude 6.83. So those are the two numbers I'm going to pull off of this table here. Let's go back then to my spreadsheet, and let's enter these values in. See, I've already forgotten what my latitude longitudes were. 40.621, 40.621, and negative 111.904. Pretty sure that's what it was. And this was 2475 years. 904, yep. Okay, PGA 0.636. So I'll enter that right here, 0.636 G's. Moment magnitude was 6.83. That was the mean magnitude. I'll leave it at an automatic FPGA calculation for my site amplification, and let's just assume that we have a site class D. Okay, right now we say that we have both a gradient of 1.5% and also a ratio here, L over H, for free face of 16. And so let's just assume for this problem that we're going to analyze a ground slope case. So we're going to set this to 0, and let's analyze it. Let's say that we had like a 2.5% gradient, which probably isn't too far off considering the slope there in the Salt Lake Valley. Okay, next, we got all that stuff input, and let's pretend that the data that's here in the CPT is the data that we're analyzing. The next thing we need to do, if you remember now from our simplified performance-based methods, we have to get the reference values from the maps that we developed. Now, rather than go and picking off values from physical maps, what we're going to do, or I'm going to introduce you to the Tethys, the Tethys app that we developed at BYU. Now, I really have to acknowledge Dr. Dan Ames, Dr. Jim Nelson. They're actually water engineers, and they use the server Tethys to develop apps with support from NASA to do flood modeling and flood forecasting all over the world. It's really an amazing tool because even individuals in very, very poor countries have free access to these high-powered maps through the internet browser. So we were able to use the Tethys server to host all of our reference parameter map stuff on it. And it's been a tremendous resource. So thank you very much to them. And also thank you to a PhD student named Riley Hills, who's been helping us with this project as well. So if I click on this button that says Reference Map Database, if I zoom out, you see that it's a map of the United States. There's a little table down here that has different values. You have when it says year, this is the year of the USGS model. So the first maps we developed used the 2008 USGS seismic source model data. We've updated currently, I think, 7 states who funded this research. They're shown down below here, in using the 2014 USGS seismic source model data. We're in the process of mapping the entire United States with this 2014 data. So even though if you're sitting here, for instance, in California, going, wait, I want to use this tool, I used to say, hey, I'm sorry, folks from California did not fund this research. We didn't develop maps for California. Hey, you're not very far away now from you folks in California or up in Washington having access to these amazing tools here. So let's, up here in the top it says, do we want reference data for the standard penetration test? We don't. We want it for the cone penetration test. Right now we have it called out which states are available, and eventually this tab will go away because we'll have data for every state, but right now we only limit it to certain states where we have data. We're interested in the 24-75 year return period, so I could manually go in and enter my coordinates, or I could come in here and manually zoom in. So let's say that there's the bridge right there I'm interested in. So I put my finger right over it and I just click. And now you see it populates a row of data in here. It puts the coordinates, it puts the all the reference parameter values. So this CSR ref, this is for the Boulanger and Idris simplified performance-based method. This Q required site, this is for the Koo and others Robertson and Ride performance-based triggering method. Then we have volumetric strain for the Koo and others method, that's Robertson and Ride. Volumetric and strain B and I, for that's Boulanger and Idris. Shear strain for Koo and others, Robertson and Ride's data, and then Boulanger and Idris shear strain. So all of these for these, let's see, these first two are for liquefaction triggering, these next two are for settlements, and these last two are for lateral spread displacements. So then comes the fun part, right? We get to enter our values in. So I wish there was an easier way to do this, but I'll take it as it is. So I'm just manually entering in all of these values as into the spreadsheet as they are reported here. 2.316. For B&I, it's 3.277. For shear strain, 12.199. And shear strain for Boulanger Idris, 28.845. Okay. So technically we're done with that map, but we may hang on to it for a minute if we want to play some more. Okay, now let's say we're ready to rock and roll for the performance-based methods. In fact, we've got everything in there that we need for performance-based. Let's say that we wanted to do a comparative analysis, a simultaneous analysis of a deterministic assessment, so a scenario-based assessment. So if I was analyzing, for instance, a single fault, I did my own seismic hazard analysis, I got my own PGA, my own side amplification factor, my own magnitude, all that stuff. I could calculate whatever I wanted to do. So let's go ahead though and let's just say let's do a pseudo probabilistic assessment, which means we're going to put in the same stuff that we grabbed from the deaggregation, but we're going to, instead of analyzing the probabilistic ground motions in a probabilistic manner, we're going to analyze them in a deterministic manner. So we get a lot of questions from folks on this cell of percentile. This is the percentile of the liquefaction triggering assessment. Okay, so the deterministic, think of this as 1 minus the probability of liquefaction. If I, let's see if this works. Okay, it worked. Think of this as equal to 1 minus the probability of liquefaction. So if Boulanger and Idris, for instance, say my deterministic triggering curve corresponds to a probability of liquefaction of 15%, then in that percentile you'll write 1 minus that probability of liquefaction. So that's why it says 85 for 85%. Okay, hopefully that makes sense. And really, the reason we wrote it this way is because we're calculating the 85th percentile liquefaction triggering data. That's really what probability of liquefaction means. If you take 1 minus a probability of liquefaction, it's the percentile of the data that you're looking at. So, okay, so we've got all our inputs in here. Now we go to basically Captain Cook's chair here, and we can now steer the ship wherever we want to go. There's lots of different options here. This little panel is where we turn different things on or off and make the assessments what we want to analyze. So if we want to analyze liquefaction initiation and settlement, they're a package deal. It's not one or the other. You just get them both. You can put true, or we could put false, whatever we wanted. But we'll analyze them both. If we want to analyze lateral spread, same thing, true or false. We can turn on or off different methods. So this is the Ku and all method. This is the Boulanger and Idris method. Right now we've got them both turned on. For lateral spread, the same thing, Ku and others, and Boulanger and Idris. And then we can specify what we want our liquefaction triggering data to look like in the output. Do we want it in terms of factor of safety, or do we want it in terms of probability of liquefaction. So you can specify that. And then for deterministic options, we can also turn different things on or off. So right now we've turned everything on. We're getting the whole package here. And then in this bottom square, we can do optional CPT modifications. And you may recall a couple lectures ago, I talked about these. These are modifications that we can do to the CPT to correct for different inaccuracies that we believe are measured, because the CPT is really an imperfect tool. So we have things like thin layer corrections, we eliminate transition layers, we can so these for instance would apply to all effects. The ones that are just specific to settlement is the depth modification, and then we have some that are just specific to lateral spread. So you notice there's two soil depth modifications. So maybe you want to account for soil depth for settlement, but not for lateral spread. So you can turn though all those things on or off. Right now we've got everything turned on. Later I'll come and turn them off, and you can see the effect that these things have when you turn them on and off. And because they're turned on, by the way, it will also lengthen the amount of time it takes for the analysis to run. Behind the scenes here, when we actually run this thing, there's millions and millions of calculations going on. So just, I guess, sit and sip on your drink and enjoy it, and be grateful the computer's doing all that hard work for you. It'll take a few seconds, and then it'll give you a notice that the analysis is complete. So let's go ahead and just for the heck of it, I'll save the file in case things crash. I've gotten into that habit, and I'll hit the Analyze button. So it's always going to give us a warning right now. We programmed it to give us this warning that basically the validity of this analysis depends on the accuracy of the liquefaction reference parameter values that you stuck in here. If you put in the incorrect reference parameter values, your analysis is garbage. We said it in a nicer way. It will be invalid, but really it'll be garbage. Hit OK, and then you see the little blue circle thing, thinking. It's performing millions of calculations right now, and it will take a few seconds to run. But once it's completed, it gives us this nice little message here. It says the simplified performance-based analysis is complete. Now once I click OK, what's going to happen is it's going to take me to this final summary page down here automatically. And on this final summary page, we formatted it to be basically really nice looking when you print these things out. So I know a lot of engineering firms, they like to print things out either as PDFs or hard copies to put with different files and packages, and we try to create the spreadsheet to be sensitive to that. So all of the data associated with the site is recorded up in the header, and you can see the plots of QC, sleeve friction, pore pressure. You can even see what we assumed was the water level, the computed I sub C. Now, if we keep moving over, what we see here, this is Q required. So this is the corrected CPT tip resistance required to prevent liquefaction at the return period that we're interested in. And you can see the different colors that we got here. So right now we're plotting the Boulanger and Idris data, you can see here. And again, I'm so colorblind I can't even see anything else, but it looks cool to me. Over here now we have the CSR and the CRR curves. So anywhere where the CRR is less than the CSR are the layers that we're going to predict liquefying. Okay. Anywhere where the CRR is greater than the CSR, then we say no liquefaction. Places where there's no CRR data at all are the layers that were removed from the analysis, either from the layer correction methods we specified, or the computer program determined that those layers were not susceptible to liquefaction. So everywhere where these dots appear on this next plot, those are where we see corresponding factor of safety values less than 1. If I keep moving over to the right, then we see the different settlement plots. So for Boulanger and Idris's method, we see settlements on the order of almost 3 inches. For the Robertson and Ride, the Koo and others method, it's predicting no settlement. So it's useful to analyze multiple models and not just rely on one, because now we have a range of predictions that we can use to base our engineering judgment on. And it's always nice when multiple models line up and give us reasonable results. And I would say within 3 inches of each other, this is pretty reasonable. I've seen cases where you get really big differences, and hopefully, you know, that doesn't happen too often, but it can. And then scooting over here more to the right, again we see the results of lateral spread. And here's a table that summarizes those results. Our deterministic assessment, which is really, for this case, a pseudo-probabilistic method, we predict 2 inches from the Boulanger and Idris method and about ½ of an inch from the Koo and others method. From our simplified performance-based approach, you can see the numbers are a little bit different. Okay. So these are the plots, by the way. These ones that say simplified performance-based. This is from the performance-based method, and the ones that say deterministic are from the deterministic method. So pay close attention to that. So right here, these are simplified performance-based. If I want deterministic, I just scroll down, and it gives me the deterministic prediction. So you can see from deterministic, both methods line up at right about 2 inches. So I mean, we're within the range, right? In the simplified performance-based, one gave us 0, one gave us about 3. The deterministic or the pseudo-probabilistic gave us about 2 inches of predicted settlement. So yeah, I mean, we're right there within a pretty good alignment and range between all these different methods for this particular site. And that won't always be the case. There's some sites where the deterministic and the performance-based are very, very, very different. Now let's go back to the input page, and just for kicks and giggles, let's turn off all of these different corrections that we have on, and not do any modifications to the CPT, and show you what happens. Now the first thing you're going to see is the time for analysis should be much quicker. So I should get the warning message like I got before. We waited several seconds before, and this time it happened in less than half the time probably. So, you know, all this stuff with QC and F sub S and U, you know, these should be pretty similar. Now, they may look different, but just remember that the scales on the plots sometimes change automatically. The data should be the exact same here. If I come over here now, though, and I look at, for instance, the CSR data and the factor of safety data, I see a lot more lines and things, which tells me that a lot more soil now is predicted to liquefy. And I definitely see that here. With the total settlement, I'm predicting all the way up to 10 to 15 inches or so, where before I was getting like 3 inches. With lateral displacement index, I'm up to about 150 centimeters, so about 1.5 meters or so, and we convert these, by the way, are always in centimeters. You should be aware of that. but with the deterministic values here, we convert them to the units you're interested in. So these are in inches. You can convert those to feet on your own if you'd like. You can see that it's pretty substantial for how much lateral spread we're predicting. Over here, you can look at our settlements, our CSRs, factors of safety. We're well over 10 inches now predicted settlements for our deterministic or our pseudo-probabilistic method. What about for, we got pretty reasonable values between the pseudo-probabilistic and the simplified performance-based lateral spread for both of these, so that's pretty reasonable. But I mean, you can see the huge effect that turning on those optional CPT correction those optional CPT corrections can have on your analysis. Just so you can see what these things look like, if you go into any of these other pages that say like PBEE liquefaction initiation, for instance, you can see that this is what everything looks like. So here's, for instance, here's all those delta terms to apply for the correction of the CSR in the simplified performance-based method. And if you were wondering why, for instance, the Koo and others method looked goofy over there, it's because we're getting some num errors in this table for some reason. So I'm going to go and debug this afterwards when I find out what caused that for the Robertson and Ride method, but because that's what's causing this Robertson and Ride method to give us some funky values here. But the Boulanger and Idris one seems to be working fine. If we go over and look at settlement, similar kinds of things, you can just come out here and check out the data for the lateral spread. Same thing, you can come in here and look at all the equations, everything. You can't change anything manually, but you can come in here and look at the equations. So everything is mapped to everything else, and so if you wanted to go into data, for instance, formulas, and well, I guess it turns off the trace dependence if you've protected the spreadsheet. So I guess you can't do that, but you can trace them yourself up in the equations and hunt things down if you're confused what's going on. So we try to keep as much out of macros as possible so that everything was as transparent as possible. Okay, well, that's basically an introduction to this spreadsheet. And if you want to download a copy of the spreadsheet, you can go to the email that you'll receive if you're part of the DOTs who sponsored this. The project manager, David Stevens from UDOT, will send you an email with all the information necessary to download this. This spreadsheet should also be available for download from UDOT's website if you go in and search that. But what I'm going to do is down in the description box, I'm just going to paste a link to download the spreadsheet directly from the cloud, and you can download it that way and feel free to use it and apply it in your projects. Now, as I said, right now, currently the spreadsheet can only be used in the states for the CPT, at least, in the states of Oregon, Utah, Connecticut, and South Carolina. But within the next year or so from the date this was recorded, this was August of 2021, by next summer, by summer of 2022, we should have all the data for all 50 states in the U.S. In that Tethys app. And this spreadsheet should be applicable to every state in the United States. All right, folks, this is all I've got for you right now. So feel free to give this a whirl, have some fun trying it. If you have any questions, feel free to shoot me an email at kevin_frankie@byu.edu. You can look me up on the internet if you want to get that email again. And I'd be happy to answer your questions. So thanks for your attention. Thanks for watching this series. And hopefully this was useful and beneficial to you. And hopefully you have some new tools and resources now that will be very beneficial to your practice as well. So have a great day, and I look forward to seeing you again in another lecture.